Have you ever heard of a ghost that passes right through you, right through walls, right through the entire planet Earth without leaving a trace? Well, believe it or not, trillions of these cosmic ghosts are streaming through your body every single second. They're called neutrinos, and they are one of the most mysterious and fascinating particles in the entire universe. What makes them so ghostly? For starters, they have almost no mass. They're so lightweight that for decades, we thought they had no mass at all. They also have no electric charge, which means they don't get pushed or pulled around by electromagnetic forces like most other particles do. Imagine trying to catch a puff of smoke with a butterfly net. It's kind of like that, but infinitely harder, because they barely interact with anything. Neutrinos can travel for light years through dense stars and galaxies without ever hitting a single atom. This makes them incredible messengers from the cosmos, but it also makes them infuriatingly difficult to detect. So, how do you catch a ghost? Sorries. You don't. You build a trap so massive and so sensitive that you can catch the 1 in a trillion chance of a neutrino actually bumping into something. And todo, that you have to go deep. I mean, really deep. Scientists build these detectors far underground, in old mines, or even submerged under immense bodies of water or ice. Why? To hide from everything else. The surface of the Earth is constantly bombarded by a storm of cosmic rays-other particles from space that would create a deafening background noise. By going deep underground, we use the Earth itself as a massive shield, filtering out all the unwanted chatter and leaving a quiet space to listen for the faint whispers of neutrinos. One of the most famous methods involves something called Cherenkov radiation. Picture this: a gigantic tank buried a kilometer underground, filled with 50,000 tons of ultra-pure water. This is the Suprakamiyokandi detector in Japan. The walls of this colossal cavern are lined with over 13,000 golden, bulbous-sized, incredibly sensitive light detectors called photomultiplier tubes. Now, imagine a single neutrino, after traveling for millions of years from a distant star, finally happens to collide with a water molecule inside this tank. The impact creates a new, charged particle that shoots off through the water, faster than the speed of light in water. Yes, you heard that right. While nothing can go faster than light in a vacuum, light itself slows down when it passes through a medium like water. This superluminal particle creates a sort of optical sonic boom. Beautiful, eerie cone of blue light, called Cherenkov radiation. The thousands of electronic eyes on the wall capture this faint flash, recording its precise timing and location. By analyzing the shape and direction of this light cone, scientists can reconstruct the path and energy of the original neutrino that caused it. It's like cosmic detective work on a subatomic scale. Another clever technique uses instead of pure water, these detectors are filled with a special liquid that gives off a flash of light, or scintillates, whenever a charged particle passes through it. When a neutrino interacts inside this liquid, the resulting particle creates a burst of light that is immediately picked up by sensors. These detectors are fantastic for studying neutrinos from nuclear reactors, or even from radioactive decay within the Earth itself, giving us a unique way to map our planet's interior. But what if you want to go even bigger? To hunt for the most energetic, most elusive neutrinos from the most violent events in the universe, you need a detector of truly epic proportions. Welcome to IceCube, one of the most extraordinary scientific instruments ever built. Located at the South Pole, IceCube isn't a tank. It's a cubic kilometer of solid Antarctic ice. Scientists drilled 86 incredibly deep holes into the ice sheet and lowered long strings of light sensors, creating a three-dimensional grid that turns a massive chunk of our planet into a neutrino telescope. When a high-energy neutrino smashes into an atom in the ice, it triggers a cascade of particles and a streak of that same blue Cherenkov light, which zips through the pristine ice for hundreds of meters. The sensors map this light trail, allowing scientists to pinpoint where in the sky the neutrino came from. A similar project, KM3NET, is doing the same thing in the deep, dark waters of the Mediterranean Sea. These giant telescopes aren't just looking for neutrinos. They're using them to look at the universe. And what a universe they reveal. These ghostly particles are born in the most extreme places imaginable. The vast majority that pass through us come from the heart of our own sun. Deep in its core, nuclear fusion reactions that power the star release an unimaginable flood of neutrinos. For decades, our models of the sun predicted a certain number, but our detectors only saw a third of that. This mystery, known as the solar neutrino problem, was eventually solved by the discovery that neutrinos can change their flavor or type as they travel, a mind-bending quantum trick that won a Nobel Prize and proved that neutrinos do in fact have mass. Neutrinos also serve as cosmic eyewitnesses to stellar death. When a massive star runs out of fuel and collapses under its own gravity, it explodes in a cataclysmic event called a supernova. 99% of the supernova's immense energy is blasted out into the universe in the form of neutrinos. These particles escape the dying star's core hours before the light from the explosion does, giving us an early warning and an unprecedented look inside the fiery heart of the blast. In 1987, a handful of neutrinos detected on Earth from a supernova in a nearby galaxy heralded the birth of neutrino astronomy. Beyond our galaxy, the most violent events in the cosmos, like supermassive black holes, stars, or the collision of neutron stars, believed to be cosmic particle accelerators, flinging out neutrinos with energies millions of times higher than anything we can produce on Earth. IceCube was the first to detect these ultra-high-energy cosmic neutrinos, opening a brand new window to the high-energy universe, and helping us identify the sources of these powerful cosmic rays that have puzzled astronomers for over a century. Even our own planet is a source. The slow radioactive decay of elements deep within the Earth's crust and mantle produces a steady stream of By measuring these, we can better understand the engine that drives plate tectonics and generates our planet's magnetic field. From the core of our sun to the edge of the observable universe, neutrinos are the ultimate cosmic messengers. They travel in straight lines, undeflected by magnetic fields, carrying pristine information from the heart of celestial objects that are otherwise completely hidden from our view. Each time one of these phantom particles deigns to interact with our detectors, it delivers a tiny puzzle piece, a clue to solving the deepest mysteries of the cosmos. We're learning about the fundamental laws of particle physics, the life cycle of stars, the most extreme environments in the universe, and even the inner workings of our own planet. These ghost particles, once thought to be nothing, are proving to be the key to understanding almost everything. Thanks for watching, and if you enjoyed this journey into the invisible universe, be sure to like, subscribe, and hit that bell for more cosmic adventures.